All right, have you ever seen something that looks like pure magic, but it turns out to be just really cool science? Well, that's exactly what we're diving into today. We're going to look at this solid piece of metal that seems to just melt in the palm of your hand. It's wild. So, check this out. This is the puzzle, right? It looks solid, you'd think it feels solid, but the second it touches skin, it turns into a liquid. So what's the deal? Is this some kind of trick, or is there some amazing science at play here? Okay, so the star of our show today is this element called gallium, and it's this really soft, silvery metal. I mean, it's so soft that at room temperature, you could literally cut it with a knife. But honestly, that's not even its coolest trick. So, to figure out this whole gallium mystery, we've got to zoom way, way in. I'm talking down to the atomic level to understand the secret world of particles. And that all starts with the basics, right? The three states of matter. You know the drill. Matter pretty much comes in three main flavors: solid, liquid, and gas. Now, the most important thing to get here is that when something changes state, like, say, an ice cube melting into water, it's a physical change. It's not a chemical one. The water is still water. The molecules are all the same, they're just acting differently. Okay, let's start with solids. Imagine all the tiny particles in a solid are like people packed into a movie theater for a sold-out show. They're all locked into their seats, right? They can't just get up and walk around, but they can still kind of fidget and vibrate with excitement. That's exactly what's happening in a solid. All those particles are just vibrating in a fixed spot. All right, now what about liquids? Well, in a liquid, those particles have gotten a little boost of energy. It's like the movie's over and people are getting up from their seats. They're not totally free yet, but they can move around and slide past each other in the aisles. And that freedom, that's why liquids can flow and take the shape of any container you pour them into. And that brings us to gases. Now, the particles have so much energy, it's like everyone has burst out of the theater doors into a huge open field. They're just zipping around, super fast, really far apart from each other. They've completely broken free. And that's why a gas will expand to fill any space you give it, no matter how big. So, you might be wondering, what's the magic ingredient? What's the trigger that makes a substance jump from a solid to a liquid or a liquid to a gas? Well, it all comes down to one simple, powerful thing: energy. And the kind of energy we're talking about here is called thermal energy. Now, it's easy to just think of this as heat, but it's a little more specific than that. It's the total energy of motion, the kinetic energy of all the particles in a substance put together. So, think about it. When you add this energy, the particles don't just feel hotter, they literally start moving faster and pushing farther away from each other. And that right there is the key. That's the engine that drives the change of state. It's the whole reason a solid can turn into a liquid, and a liquid can turn into a gas. Okay, so here's a really important little detail. Thermal energy is the total energy of all the particles, right? But temperature, that's just the average energy. Kind of like the total wealth of a country is one thing, but the average income is another. Temperature just tells you how much energy the average particle has. All right, so if adding energy is the key, you have to ask, when does it happen? At what point do these particles get so worked up that they actually change their state? Well, it turns out every single substance has its own unique, specific tipping point. Let's just take water, because we all know how it works. You add some energy, some heat, to a block of ice, it eventually hits its melting point, which is 0 degrees Celsius, or 32 Fahrenheit, and boom, it becomes liquid water. Keep adding that energy, and it'll get to its boiling point, 100 Celsius, and turn into steam. But get this. This is where things get a little weird. Let's say you put a thermometer in a cup of melting ice. You're adding heat, right? The temperature goes up, and then it just stops. It gets stuck right there at 0 degrees Celsius. And it will not move, not even a little, even though you're still pumping heat into it. So, what's going on? Well, what's happening is that the energy you're adding has a new job. Its priority has changed. Instead of making the particles jiggle faster, which is what raises the temperature, all that energy is being used for one thing: to break the bonds that are holding those particles together in their solid shape. It's like it's busy unlocking all the little connections. And only when every single bond is broken, then the temperature can start to go up again. All right, we've talked about particles, we've talked about energy, and we've talked about these tipping points. I think we have all the clues we need now. So let's circle all the way back and finally solve this gallium mystery. Okay, so here's the solution. Your hand, it's naturally warm, right? It's basically a walking source of thermal energy. So when you place that solid gallium in your palm, the heat from your hand just floods into the metal. The gallium particles soak up all that new energy and start vibrating like crazy. And pretty soon, they hit their tipping point, which for gallium is a very, very low melting point. The warmth from your hand is more than enough to give those particles the energy they need to break free and turn the whole thing into a liquid. See, it's not magic at all, it's just pure physics. And of course, this whole thing works in reverse too. It's a two-way street. If adding energy causes things to melt, well, it makes perfect sense that taking energy away would do the opposite. It's this really beautiful, complete cycle. When you add energy, you get melting and evaporation. When you lose energy, you get condensation, like when your cold drink gets wet on the outside and you get freezing. This whole dance that matter does is just driven by this simple back and forth of energy. And here's one last little cool fact for you. A substance's freezing point is the exact same temperature as its melting point. They're identical. For water, we know that's 0 degrees Celsius. It's the same tipping point, the same magic number. It just depends on which direction you're going, adding energy or taking it away. So I'll leave you with this one last question to chew on. We all know that lava is liquid rock, right? It flows out of volcanoes. But now that we know a substance's state is all about its energy and its unique properties, what state do you think that rock is in when it's still deep inside the earth, before it ever erupts? Definitely something to think about.